All right, welcome to States of Matter and the Gas Laws. We're going to need a reference table, we're going to need a calculator, and let's get going. So the first, well actually, there are 5 states of matter. There are 5 phases of matter. There's the solid, liquid, and gas we're going to talk about. Then there's Bose-Einstein, condensate, and plasma. We're not really going to be addressing those last 2, but feel free to research those on your own if you're interested. So let's focus on solids, liquids, and gases. So when you have a solid, like your phone or, block of wood or something, the volume of that object is definite or fixed. It's not going to change. Depending on, you can do anything to it, but the volume will stay the same. The shape of your object will also not change. It's a definite or fixed shape. You cannot compress the solid particles together. And if you were to draw what we call a particle diagram, you would notice that these particles are very close together. They're jammed right close. There's tiny spaces in between, but really they're very, very close. And they're just vibrating. They're not moving too much, they're just vibrating. Okay? Excuse me. The forces of attraction between these particles are very strong, and the molecules are held in a rigid position. So the force of attraction is very strong with a solid. A liquid. So if you have, let's say, 50 milliliters of water in a grad cylinder, and you pour it into another grad cylinder, you should still have 50 milliliters. So you might lose a little bit because of transfer, but the volume of that liquid should not change. It does not change. The shape of that liquid, however, does change. That's how we can make ice cubes in different molds, or just, heck, an ice cube itself. Because a liquid takes the shape of whatever container it's in. However, its volume remains the same. The particles of a liquid cannot be compressed together, although, if you look in our picture, the particles of a liquid are a little bit further apart this time. They're not closely packed like in a solid. So because of that, we can say that they have moderately strong intermolecular forces, and it allows molecules to flow over each other. So they're not so tightly packed. They're a little bit weaker. They're moderately strong in a liquid. Gases. So gases are very unique because they take the volume of its container. So if you put a gas into a balloon, tie the balloon off, the gas particles are going to fill the balloon and take the volume of that balloon. If you put a gas in a 1 liter Erlenmeyer flask with a stopper, the gas is going to fill up the whole stopper, and it's going to take the volume of 1 liter. And if you put that same gas into a 2 liter flask with a stopper, it would be the same. It would go to the 2 liter volume size. So it takes the volume of the container, and it also takes the shape. So let's say you take those gases and you put it into a cartoon balloon of a certain shape. And so it will fill up that shape. The reason why is because the particles are so far apart, you could finally compress them together. And this happens in pistons, sometimes in your car engine, or if you're playing like a trumpet or one of those instruments where you push down a piston, the gases, the exhalation can be compressed together. So gas particles should be very far apart. And that's because they have very weak intermolecular forces. So, let's just say you have helium in a balloon, you release the helium from the balloon, those helium molecules are just leaving. They're not coming back. They're moving apart and will stay apart because there's nothing holding, or very weak forces holding them together, shall I say. All right, now let's go to reference table A. On the regular reference table. If you're in the honors class, you'll also need to go to the honors reference table, A. So remember how we were talking about how gases are affected by conditions of volume and of size? They are also constrained by pressures. So these are our standards, units of pressure. These first 2 are on the regular Regents reference tables. And these last 2 are honors only. So you don't need to worry about that. Let me just show you for a second. So here we are on the regular reference table. You see here, standard pressure is in kilopascals, 101.3, and atmospheres, which is 1. That's standard pressure. STP, we're taking the T out of it. If you're in the honors class, you'll find on honors table A, you'll find standard pressure in atmospheres. So that would be 1 atmosphere. You'll find 101.3, you'll find 760 millimeters of mercury, and you'll find 760 torr. If you're in the regular college prep, you won't need to worry about those other 2 values. But for the honors class, know where to find it. So those are all the standards. Thank you. So let's do some practice. Let's do some conversions. So convert 206.4 kilopascal to torr. So we have all our conversion factors right here, okay? 206.4 kilopascal. Now, we need to go to torr. We seek torr, we know kilopascal. So I go ahead and I look up here. I see 101.3, I see 760. So now, and you could put this over 1 if you want. So let's do 206.4 times 760 divided by 101.3, which gives you an answer of 1548.509, blah, blah, blah. If you were to round this to something, you shouldn't have all those decimal places. If we were rounding to significant figures, it would be 1549. But if you're not rounding to sig figs, you can just keep it as maybe 1548.5, or that would be fine. Your units would be torr. Okay. Let's try another one. Hold on a second. Just a second. .653 atmospheres to kilopascal. So we have 0.065 atmospheres is our given. We seek kilopascal, we know atmospheres, so 101.3, 1. So all you got to do is multiply across. 0.653 times 101.3 is 1489, which rounded to sig figs would be 66.1 kilopascal. If you're not rounding to sig figs, don't worry about it. One last one, I guess. Hold on a second. I'm looking in my regular Regents book. And, okay, so this is the honors one. And then I have a Regents one, which is 847 kilopascals to atmospheres. I'm going to do both. Stay with me here. So if you're in the honors class, your book says 847 millimeters of mercury. So we're going to do 760 millimeters of mercury is 101.3 kilopascal. If you're in the college prep, it says 847 kilopascal. And so we'd go away from kilopascal and we'd go to atmospheres. So now let's do that math. In the honors book, it's 847 times 101.3 divided by 760, which should give you 112.896, which would be 113 kilopascal. If you're in the college prep, 847 times 1 divided by 101.3 gives you 8.3613, blah, blah, blah. How about 8.36 atmospheres? Okay? The practice is the same. Okay? All right, let's start talking about some phase changes. Phase changes. Obviously, our phases don't always remain a solid, a liquid, or a gas. We can have changes. So let's define some of those changes. Boiling point. The normal boiling point is when the temperature of a substance rapidly changes from liquid to gas at standard pressure. So boiling is liquid to gas. Now, think about it. Liquid to gas, in order to boil, you need to take heat in. So this would be an endothermic reaction, or excuse me, process. Endothermic. Condensation is the temperature at which a substance goes from gas to liquid at standard pressure. So gas to liquid. This is giving off heat. This is an exothermic process. The boiling point and the condensation point will be the same temperature. Oh my gosh, that is really messy. Same temperature. Okay, so if you go to table, oh my gosh, and it's crooked, I'm sorry, table S. So when it says boiling point, you might also want to, oh my goodness, sorry. You might also want to write condensation point right next to boiling point because they're the same temperature. Okay? Freezing is a temperature in which a substance goes from liquid to solid. It's standard pressure, liquid to solid. Now, when you go from liquid to solid, think about rain turning to snow. We're giving off heat. That's exothermic. Melting is when you have solid going to liquid. So solid going to liquid, when that snow melts and becomes liquid water, that's going to be taking heat in, endothermic. And guess what? The freezing point and the melting point are the same temperature. So if you go back to your reference table, melting point is the same as freezing point. I don't recommend writing it, crooked like me. I would write it the correct way on your reference table S. Normal point is when that phase change occurs. So standard pressure, 101.3 kilopascal, 1 atmosphere, 760 torr, 760 millimeters of mercury. I believe the last thing we're going to do today in our notes is entropy. Entropy. Entropy is the amount of chaos or disorder. In the honors class, we'll talk about that being delta S, but really, we don't need to go into that right now because we don't go that far. Nature favors high entropy because less energy is required to maintain it. Think about it. If you go on vacation over the summer and nobody mows your lawn for 2 weeks, the lawn is going to be crazy. There's going to be weeds everywhere. It's going to be high grass. It's going to be all over the place because you didn't put in any energy to maintain it. And nature just did what it wanted. If you think about a golf course, you think about how expertly manicured all the greenery is, and the sand traps are nice and raked. I don't golf, so go with me here. That takes a lot of energy. Somebody is out there every day either mowing or weed whacking or raking or fertilizing or watering or something, keeping that pristine condition. So nature would rather just say, what the heck, let's just let it go. So a messy room where you just throw stuff everywhere, that would have high entropy. Disorder, chaos, randomness. In order to keep your room nice and neat and orderly, it's going to take energy. It's going to take time for you to arrange your books and straighten off your couch and clear off the table and dust and vacuum or mop or whatever. So nature favors high entropy. So the next time your mom or dad says, hey, clean your room, just say, I'm sorry, I'm like nature, and nature favors disorder, and so I'm just allowing nature to take its course. Okay? I don't know if that's going to work, but you can try it. I think we're going to wait on that one. Okay? Thanks for watching.